All right, well, here we are again. So today we're going to carry on with chapter 4, and most likely we'll do a large percentage of chapter 5. Now, I do want to remind you, if you've forgotten all about it, that because there was no spring break, the school is giving out a handful of days off. Next Wednesday happens to be one of them. So that means we will not meet next Wednesday. So you'll have a week off from pre-calculus. And so now, if I accidentally forget and send you a reminder for the meeting, just forget about it. We're not having class next week. Let's see, officially next Wednesday, the 14th, is a day off. In fact, let me just double check something real fast. It's listed here. Let's see. Here we go. The 3 days that are off were Tuesday the 23rd, Wednesday the 14th. Of course, that's next Wednesday, and then finally Monday the 3rd. So you're off on next Wednesday. Woohoo! There's a week off from pre-calculus. So we'll just carry on today with chapters 4 and 5, and then when we get back, we'll carry on. And so I just wanted to remind you now rather than later that we're off next week. And so now what we're going to do, like I said, is just carry on with where we left off in chapters 4 and 5. We're about maybe halfway through 4, and then we'll move into 5 and get as much of it done as we can. So you might remember that last time we introduced logarithmic functions, and this is the basic form of a logarithmic function. And what we noticed last time is that unlike the other functions we've seen up to this point, x is actually the exponent, okay? That's something you don't normally see. So that's what makes this function so unusual. It's also the reason why the function grows so quickly, or else it decays so quickly, because x itself is the exponent, which means it's growing or shrinking over time. A is the initial value of the function, which means that when x equals 0, the function has a value of 0, or a rather. This is the starting point. And then b is the base, okay, which can have any value except 1, because if it's equal to 1, then we just end up with a constant. Okay, it can't be 0 either, of course, because then the function would just be 0. Okay, so the only thing we're ruling out is a value of 0 or 1 for b. A can have any value, and of course, x can also have any value. We saw a few examples of this. Let's see, there's one. Okay, so y equals 3 times 2 to the x power. All right, and of course, you can see that because a is positive, y can only be positive. So while the domain is all the real numbers here across the real number line, x can be anything, y in this case can never be negative. It also can't be 0. Okay, there's no value of x that would cause this function to be equal to 0. So the domain is all the real numbers, but the range is all the positive, non-negative real numbers. I guess you could say positive real numbers. And then if a is negative, I think we have an example of that here. If not, we can go to Symbolab and look at one. Let's see. I think we have one here that illustrates decay of a radioactive element. And let's see, where is that? There, no, that's not it either. All right, all right, I'll tell you what, let's go to Symbolab and find one. All right, so we don't have to get too carried away. Let's just use this the same exact example, except that this time a will be -3. Okay, so we'll have y equals -3 times 2 to the x power. All right, let's see what this thing looks like. All right, so you can see now it's the other way around. Basically, the two functions are mirror images of each other, where the horizontal axis could be thought of as the mirror. So you can see here, the function never quite reaches 0, does it? And it certainly never becomes positive. So while the domain is the entire real number line, the range is everything, all the negatives up to but not including 0. So the range is what we could say is just simply all the negative real numbers. Okay, now, oh, and one more thing, the y-intercept is the point 0, comma a, and y equals 0, the horizontal axis, is an asymptote of the function regardless of whether a is positive or negative. All right, now what are we using this function for? It lends itself very nicely to cases where growth takes place on what we call an exponential basis, which basically means it's growing very, very quickly. Like if you recall from high school biology, how quickly a bacteria colony grows, that would be described by exponential growth. Here we have two examples of a painting where in one case, the painting is growing at a linear rate, and in the other case, it's growing at an exponential rate. So painting A is growing at a rate of $2,000 per year, growing in value, that is. And then B is growing at a rate of 2% per year. So A is described by a linear function, as you can see. It starts out today when time equals 0 with a value of $100,000. And then every year that goes by, the value goes up by $2,000. B at the same time, though, while it starts at 100,000 today as well, you can tell because when t equals 0, this function is equal to 100,000. Every year that goes by, it grows not by $2,000, but by 2%. So initially they're growing at the same rate, but as time goes by, B is growing more quickly than A. And so, of course, it takes this form. It's an exponential growth function. And if you plot them together, you'll see that initially they're very similar. But after a while, you'll begin to see that the orange one, which is our exponential growth function, is growing faster than our linear growth function. And after a while, the spread between them is actually quite considerable. In fact, when you get into year 30, the difference between the two is about $20,000. So the exponential growth will eventually be faster than the linear growth, although it takes a while before the difference is noticeable. But after a while, it should be pretty clear that the exponentially growing function is rising more quickly than the linearly growing function. Now, we can solve for the growth rate. In some cases, this is what we're really interested in. Not so much what is the future value of some number that we have today, but how quickly is this variable growing? So we had this as our first example. We saw that in 2006, there were 80 deer in a wildlife refuge. And 6 years later, the population had grown to 180. Oh, you can turn it in tomorrow. Tomorrow's fine. Yeah, if you haven't turned in your midterm yet, tomorrow is fine. Tomorrow midnight, basically, because I don't specifically remember, but that's fine. Friday is fine. If you're not quite ready, try to make sure it's done by tomorrow at midnight. Okay. Anyway, so here what we can do is we have two different values for our function at two different points in time, and we can turn this into a growth rate. So how do we do that though? Well, we've defined n of t to be the number of deer at time t, where today is 0. Yeah, just send it to my email. Just take pictures of it and send it to my email. That should be fine. Just make sure that I can read the pictures, that's all. That's the only thing I ask. Make sure I can read it. Yeah, there's no place in Moodle to put it. I don't even know how that works. Just email it to me. I'm sure there's something that could have been done, but I'm so low tech that I never did quite get it figured out. So it doesn't matter. You can just email it to me. All right, anyway, so this is what the function looks like. So it starts out as n of t equals ab to the t. Now, the only way this differs from what we were looking at earlier is that we've replaced the x's with t's. We often do that when we're looking at something that's growing over time. This just reinforces the idea that this is time, but we have to be careful with time. You don't want to use the actual year in these functions because you will not get the correct results. Instead, what you do instead is you whatever the current year is, you set that equal to 0, and then every year that goes by, t increases by 1. So in this case, for example, 2006 could be considered year 0, and 2012 would be considered year 6. Okay, great. Now, plug in your numbers. So we've got, now a, remember, was the initial value of this function, which would be 80 in the year 2006, or t equals 0. When t equals 6 in 2012, the deer population has reached 180. So we have 180 equals 80 times b to the 6th power. B is now the variable that we're looking for. It turns out b is actually equal to 1 plus the annual growth rate of the deer population. So algebraically, I divide both sides by 80. Now, in order to solve for b, what I have to do is take the 1/6 root of both sides of this equation. And the reason for that is because when you do something like that, if you have, let's say just in general, you have x raised to the n power, all raised to the m power. This equals x to the n times m power. So in our case, if you have b raised to the 6th power, which is now raised to the 1/6 power, you have b raised to the 6 times 1/6 power, which is b to the 1st, or just plain b. So that's our strategy here in raising both sides of this equation to the 1/6 power. We're simply trying to isolate the b and solve for it. Okay. So what this tells me is that 2.25 to the 1/6 power is equal to b. And whatever this number is the amount that we're looking for. So if you throw that into your calculator, you'll get approximately 1.1447. So basically the way to interpret that is that in 2012, the deer population equals 114.47% of its value in 2006, which implies the growth rate, the total growth per year equals 14.47%. So in other words, they're growing pretty fast. Okay, now you can confirm this by going back to the beginning of the problem and saying, well, listen, what if I take 80 and multiply it by 1.1447 to the 6th power? Does it give me back 180? And except for potential rounding problems, that should be the case. Why, yes, it does. It's almost exactly, like I said, with a little rounding, it's 180. So in other words, this is the annual growth rate right here. And the 6, of course, means that the deer have been in this wildlife refuge for 6 years. And so the question is how fast. Now, the reason why that's important information is because what if we want to know what the population is likely to look like, let's say 5 years from now? If we assume that the growth rate continues at the rate that it is, we should be able to predict how many deer will be there 5 years in the future by continuing to apply this rate every year for the next 5 years. So this is potentially very useful information, and we often see it used in the area of investments, because then we may want to know, if I invest in a certain type of asset like a stock or a bond, given historical information about the returns to that stock or bond, I'd like to predict what it might be worth in the future. And so I can use a model like this based on the assumption that the growth rate is exponential. If it isn't, then my forecast won't turn out very well. But if that is in fact the case, I should be able to use this to do forecasting. And I should come up with something that's pretty reasonably accurate. Now, this is one of my favorite examples because it does involve an asset, but it's not a stock or a bond. It's a silver dollar. Now, you may not be aware of it, but up until 1964, all of our coins, except for pennies and nickels, were made out of silver. Why did they have to stop making them out of silver? Because the silver was becoming too valuable. It got to the point where a quarter contained more than 25 cents worth of silver, as did a dime and a half a dollar. And the silver dollar, there do exist, by the way, half dollars and silver dollars. You may not have ever seen one, but they do exist. People hoard them. When they get them, they hoard them, and that's why they disappear from circulation. But at this point in time, all coins were made out of silver. So if you bought a silver dollar in 1899, it would have cost you $1. And in 2019, we're assuming that you could sell it in the market for $37.42, not because you could spend it for that kind of money, but because it's worth that to collectors. And you know, the silver content would be worth a lot too, but not $37.42. Most of that value is coming from the fact that it's collectible. Okay, in fact, just for the fun of it, why don't we see what a silver dollar looked like in 1899? Not bad. That's kind of a nice looking coin, isn't it? I like that. So that one, now, of course, I just made up that number. It turns out this one in particular is only worth $166. All right. But let's just say that the one we have is worth $37.42. Okay. And now, you know, a lot of the value comes down to the scarcity. How many of these are there in circulation? How many are available? That's what really ultimately determines the value of a coin. How scarce is it? And also, what kind of condition is it in? I'm sure you could find one that's worth a lot more money if it was in perfect condition, or if it was less commonly. They didn't mint quite so many of them. But anyway, let's just say that this is what's happened. What was the annual growth rate between 1899 and 2019, based on the assumption that the growth rate has been exponential? Well, in a case like this, we'll use that VT function that we had earlier. V means value. The value of time t equals a times b to the t. And you recall that in this case, t equals 0 represents 1899. So that 2019 would be 2019. Therefore, t would be 120 because that's 120 years later. We also know that the value at time 120 is $3,742. And the initial value was $1, but this is not being referred to as V1. We're calling that A in our formula. Okay, so we do some plugging in and we get a similar situation to what we had before. How do you solve for something like this? Let's raise both sides to the 1/120 power. Because we know that this one will be, algebraically, this is the same thing as b to the 120 power times the 1/120 power. And so the goal is to reduce the exponent of b to 1. All right, actually, let me clean that up a little. And that's exactly what we've done here. So whatever this number is here on the left equals b. Okay, so when you take out your calculator and try this, you'll see that the result is approximately 1.0710, and this means the growth rate is approximately 0.0710, which translates into 7.10%. That's a pretty good investment. You don't get that very often. That's pretty good. But again, it's because it's a collectible. And you never know with collectibles. It's a very tricky market. You never know what people want or what they're willing to pay for. It depends, again, like I said before, in a case like this, on the scarcity of that coin and on the quality or condition that it's in. You can find others, like if you went to the same company and said, listen, show me, I don't know, let's take a look at a gold dollar coin. Let's see. So let's say we go and get a $20 gold coin from 1899. There it is. Now we're talking. Look how expensive that is. Oh, all right. Well, maybe here's 1899. That one's, it's only 1,044. Okay, whatever. But that's a lot of money. There's all kinds of cool coins here, aren't there? Yeah. These are collectibles, but again, this market is very, very volatile. Sometimes you can make a lot of money and maybe other times not so much. Just like art, everything in this area is very, very risky. But anyway, we did also go through the all the steps needed to find an exponential equation from 2 points, which we've done before with linear equations. So if we had 2 points on this exponential function, here it's a little bit messier because the algebra involves a lot of exponents. So for example, here's our starting point. This is our traditional or standard exponential function. We know that one of the points that it contains is -2, 6. So when you're doing something like this, just be careful that you replace all the x's with -2, and f of x, which we know is equal to y, is equal to 6. So this is something that we know, but this by itself isn't enough for us to identify the values of a and b, because we have one equation and 2 unknowns. So we need a second equation to figure out what a and b are worth, or equal to. So what do? Well, we go back and try the second point, which is 2, 1. And we do the same thing. So this time, the original function, of course, is f of x equals ab to the x power. And now this is our x. This is our f of x. So 1 equals ab squared. We combine that with our previous result, 6 equals ab to the -2 power. And now we have 2 equations and 2 unknowns. And so we can figure them out with what we call substitution. Now, this can be done in several different ways. Ideally, what you want to do is take one of these equations and rewrite it in terms of either a or b. So let's say you choose this one. What I can do now is divide both sides by b squared. And I can also rewrite that, if I choose to do so, as b to the -2 equals a. Now this a can go into this expression. And that implies that 6 equals b to the -2, b to the -2. 6 equals b to the -4. And now what I can do is, there's a couple of things I can do. It might be easier if I multiply both sides by b to the 4th. Because if I multiply these together, I'll end up with b to the 0 power. Just a quick reminder, when you multiply 2 values together that have a common base, we can add the exponents. And here, when we add them, we get b to the 0 power, which is 1. And so what this is telling me is that b to the 4th is equal to 1/6. And then finally, b equals 1/6 to the 1/4 power. Kind of awkward, but that's what it's equal to. And that number itself, as we see in the next slide, is approximately equal to 0.6389. Okay, so let me go, the steps are all on the next slide. Let's jump ahead to that one. So again, we started out with this. Recall that, let me just quickly add these back here. We start out with 6 equals ab to the minus 2 power, 1 equals ab squared, which implies that a equals b to the minus 2. So what we've done here is plug that in here. And we've got 6 equals b to the minus 2, b to the minus 2, and this equals b to the minus 4 because you're adding these exponents. And then that can also be rewritten as 1 over b to the 4th. So 6 equals 1 over b to the 4th. I can cross multiply and I end up with b to the 4th equals 1/6. And then how do I get rid of this 4? I want to multiply or raise that to the 1/4 power because now I've got b to the 4th times 1/4, which is just b. And that means I've got 1/6 to the 1/4, which is approximately equal to 0.6389. Now, what do we do with that information? Remember, we had a second equation, 1 equals ab squared right here. What I can do now is solve for a by replacing this b with 0.6389 very quickly and easily. So let's do that on the next slide. Hold on one second. So given that we've solved for b and we have this equation, we can just simply replace the b with this number. And you can see that you'll end up with b squared here is 0.4082, which implies that a must equal 1 over 0.4082, which is approximately equal to 449. And since the original equation that we're looking for is ab to the x, that means we have 2.449 times 0.6389, all raised to the x power. And we're done. We've identified it. Now, that was a lot messier than when we solved for a linear equation with 2 points, but it works. It works in exactly the same way. And while we're at it, we may as well go, oh, here it is. We don't need to go to Symbolab because it's already right here. And again, since a is positive, you can see the range is equal to all positive real numbers. The domain, of course, is all real numbers. So in this case, now the reason why it's falling rather than rising is because b is less than 1. So this is a case where the growth rate is actually negative. Okay, in other words, remember the actual growth rate is equal to b minus 1. So the growth rate is b minus 1, which in this case implies 6389 minus 1. All right, so 0.6389 minus 1 equals negative 0.3611. So in other words, whatever this variable is, it's decaying at a rate of 36.11% per year, which is a very rapid rate of decay. And so the value of this thing, whatever it is, this could be, for example, the half-life, or this might be describing the amount of radioactive content in let's say, radium. You've got a chunk of radium, and you want to figure out what proportion of the total is lead versus radioactive material. That very well may be what this is doing here. It's falling off very, very quickly. All right, but it never actually becomes negative. The value can never drop below 0. Now, we saw some examples here where we applied this to interest rates. And at the end, we discovered that when interest rates are compounded on what we call a continuous basis, let's skip ahead down here, this is exactly what we've been seeing. This is our exponential function, where x is RT and P is the starting value. So when interest is compounded what we call continuously, when interest is compounded continually, the growth rate is exponential. All right, so let's say that you bought, maybe we can make up an example so you can see the graph. We can do a Symbolab graph. Oh, here's one. What if here's an investor who deposits $1,000 into a one-year account that pays a rate of 4% per year. What we'd like to be able to see is what happens to that account as the years go by, not just in 1 year, but over time. So we can go back to Symbolab and say, okay, Symbolab, let's try this function. All right, so we have A equals 1,000 e to the RT. All right, so let's call it, let's see, we started with 1,000. And then we have e to the 0.04 x. I'm not sure if Symbolab, I guess it could use t's, but I'm not positive. So I don't want to push my luck. I'll just leave it like this and let's see what it looks like. So we know it'll grow slowly at first. So now, because this is money, the one thing you do need to pay attention to here, though, is that because it's money, we can't actually have any values in the second quadrant. In other words, we can't have a negative value of x, because x would mean, a negative x would mean the past, okay, years in the past. So this is our starting point. Or at the moment when x equals 0, the time is 0, we start with $1,000. And then after that, this is how quickly it grows over time. So for example, in 20 years, you'll have approximately, let's say, $2,200. And then in 30 years, you'll have approximately $3,000, let's say, $200. So you can see it's growing very, very quickly. But because this involves money, we can ignore the second quadrant. The function that we need to know is right here. Okay, so in real world applications, sometimes we don't have the ability to use the entire function, only certain parts of it. And here's an example of that. This is only as applicable applicable in the first quadrant. That's a lot of growth, though. If your money's growing that fast, you'll be able to retire in no time. This is a very quick rate of growth. All right. Now, by the way, if you notice, every time we look at a website, look what's going to start happening. There's going to be ads for these coins that we've been looking at. So every time we go back to Symbolab, for a while at least, it's going to be continuously showing us all these wonderful coins because they think that we want to buy them. That's the way the internet works. I'm sure you've noticed that from your own experiences. You go to look at one website, even if it's not even on your computer, if you looked at an ad on your phone, you might even start seeing it on your laptop. That's how smart the internet is these days. It knows what you want, and it tries to get it to you. So look at all these ads down here. Ooh, now this one is worth a lot of money. This is almost $2,000. That's a 1933 $20 double eagle, it's called. Man, how cool is that? Whoa. I'd like to have that coin in your pocket. It just glows. Look at it. It's so cool. This is what the back looks like. The eagle flying over the sun. Nice. Okay. Anyway, so then we also have continuous decay. This involves, let's say, radioactive elements, which we do know decay at a fairly rapid rate. You might remember in high school learning about half-life, which refers to how long it takes before 50% of the element has been converted to lead. And so here, the only real difference is that the exponent is negative. It starts out positive, but then it falls off very quickly. So it's basically the opposite of what we had here. In fact, if I went back here and just changed this to negative 0.04, you'd see exactly what I mean. So yeah, you can see it also starts at 1,000, but it's falling off very, very quickly. This could be used maybe to describe the value of your car over time. Let's say you started out with a car that's worth $20,000, brand new car, and the unfortunate reality is, though, it decays over time in value because of depreciation, as it's called. So let's say that for your car, the rate at which it decays in value is 20,000 e to the, let's try negative 0.02x. This would be the graph. And again, we have to start in the first quadrant. We started at 20,000, and this is now, of course, nobody keeps their car for 20 years, but that's how the graph works. I don't know if we can adjust. Oh, all right. Well, it looks like we can zoom in, so you can just look at maybe the first 10 years would be along here, and you can see that after 10 years, it's going to be worth maybe 16. But anyway, that's how depreciation works. Then we started our discussion about logs. Now, logs basically represent ratios. It's an exponent taken from an exponential function. So in other words, if I have something like this, suppose I told you that y equals 1,000. Now, what the log does, it says, listen, given the base that you're asking for, the log itself is simply the appropriate exponent, which when applied to that base, gives us back the original number. So log base 10 of, this is the base, by the way. Every log has to have a base. So the base is 10, which implies that this whole thing is telling me that 10 to the third power equals 1,000. So basically, you're taking this expression and working it backwards and saying, what is the exponent in a case like this, given that the base is 10? Now, these logarithms are surprisingly useful in practice. They're useful for helping us describe variables that grow at an exponential rate. I think I mentioned this example once before. The Richter scale for earthquakes is based on this exact type setup. In other words, the values that you are seeing with earthquakes are actually powers of 10. So if they tell you that the Richter scale is 5, it's actually what they're really saying is that it's 10 to the 5th power, the number that they've got. So that the difference between a Richter scale reading of 4 and 5 is actually a difference of a factor of 10. Okay, so in other words, every time the Richter scale goes up by 1, the severity of the earthquake is actually increasing by a factor of 10. And that's because it's a very large number. So when we're dealing with very large numbers, it's often convenient to express them as exponents or logarithms. Or it's like pH, the pH that you learned in high school. A pH of 6 means 1.0 times 10 to the minus 6th. Okay, it's the concentration of, I forgot what it is, but it's the concentration in the solution of 1.0 times 10 to the minus 6. So the 6 simply means 1.0 times 10 to the minus 6th. All right, anyway, so how about this one? Log base 3 of 9 equals 2 because 3 squared, the base raised to this power, equals 9. Now, if you've got a calculator that you're using for this stuff, I'm not sure if the iPhone has this. Let me just go look at it for a second. You know that the iPhone has a very nice scientific calculator built into it. If you've never used it, if you go to the iPhone app for the calculator, what you have to do is make sure you turn it on its side. And when you do, you'll see this really amazing, let me show it to you, scientific calculator. Look at that. It's very powerful. It has everything you could possibly want. You just have to learn how to use it. And in fact, I see right here that it does have log base 10. So for example, if I wanted to know this one, if you use your calculator. Now, of course, if you have a more advanced calculator, this would be a little different. But on the iPhone, what you would do is say, all right, type 1,000 and then log 10. And 3 pops up in your window. It also has natural log, which we'll discuss in a few minutes. I don't see any others, though. Wow, I guess they decided that that's all you really might need. And they're right about that to a point. Most logs you see in practice are either base 10 or base E. Now, we know what E is. We've been using it throughout this chapter. E is approximately equal to, let's make a note of this somewhere, just in case we forgot. There it is. E is approximately equal to, let's see, 2.71 828 1828 459. It goes on and on forever. This is considered to be an irrational number because the number of digits after the decimal point is infinite and they do not repeat themselves. It's a surprisingly useful number in practice. It's often used, like we saw earlier, to calculate the amount of money you'll either pay or receive based on whatever interest rate you've been given. So it's very helpful in many applications. And so because of that, the log with base E has a special name in math. It is often referred to as the so-called natural log. And we spell it, instead of log, we spell it ln, so we know the difference. So your calculator, if you're using the iPhone calculator, has this one as well. Right next to log 10, you'll see an ln button. So if you wanted to know, for example, the log of 100, type 100 log, and there you go. It's approximately 4.605. And how do we interpret that? It means that It's the same thing as saying that e raised to the 4.605 power is 100. Okay, so think of those two equations as essentially mirror images of each other, the two sides of the same coin. Okay, so those are the two you're most likely to run into in practice. The base 10, which is sometimes called the common logarithm, is a very popular choice. And again, this is what we're seeing with the Richter scale and with the pH scale in high school biology. It is not that unusual for logarithms to be based on either 10 or e. These are the ones you're most likely to run into. So 10, remember, we call it a common logarithm. And e, we call that a natural logarithm. Now, we're not going to spend most of our time trying to calculate logs. What we are going to do is learn their algebraic properties, because they can come in very, very handy in helping us solve complex equations. Oh, by the way, just in the most general possible terms, this is what we're actually doing here. B is the base. And of course, if b raised to the y power equals x, that implies that the log base b of y, or x rather, equals y. Okay, so don't worry, you'll get used to it. If you haven't done this in a while, or if it seems confusing, we'll get the hang of it after we've done enough practice. It's just like anything else. Practice, practice, practice. Okay. Base answer. You can think of it that way if you want to. Sure, whatever helps you remember the stuff. Sure. I mean, whatever you have to do to memorize this or understand it, that's mnemonic devices to me are very, very helpful, because they're unique to the way you think about this problem. So in other words, you can't teach other people. You can suggest mnemonic devices to people, but ultimately each individual's memory works a little differently. And so whatever sticks, that's the one you want to use. Okay. If that works for you, then you use it. Okay. It's like, I know some of those mnemonics, I can hardly be bothered to memorize them. And yet there's others that come in very useful, like PEMDAS. Well, I don't, what happens with mnemonics is that once you understand something, you don't really need to have it memorized anyway. Or I remember when I was younger, and I guess it was in elementary school, some people needed to memorize a mnemonic device to remember the order of the planets. And I never bothered, because I knew the order of the planets. But there were certain things in chemistry and physics where it really did turn out to be very helpful to memorize mnemonics. Or like, remember in I guess it was high school physics, when you were learning about the rainbow and the colors of the rainbow, it would be very easy to forget the order of the colors. And so if you might recall, we learned the mnemonic Roy G. Biv, which stands for red, orange, yellow, blue, indigo, violet. And you can see it works so well that I still remember it all these years later. So you never know with mnemonics. Sometimes they work and sometimes they don't. But anyway, always understanding is better than memorizing, any way you look at it. Now, for any logarithmic function, the domain is restricted to strictly positive real numbers, no zeros, no negatives. The range, on the other hand, is any number, any real number. In fact, why don't we take a look at a couple of examples of this in Symbolab. Let's try y equals natural log of x, just log x. Let's see what this thing looks like. Yeah, see all those ads for coins there? Oh no, it's gone. There they are. Oh, they're over here. Okay, so you can see the asymptote here is the vertical axis. You can never quite reach the zero. There's no log that will give us back a value of 0. So y cannot be 0, but it can be, I'm sorry, x cannot be 0. Y can be anything. You can see y ranges from negative infinity up to positive infinity. It's x that's restricted to being anything strictly positive. Okay, so this function will never appear in the second or third quadrants. And the intercept is 1, 0, because the natural log or any log of 1 is equal to 0. Okay, so that's one of the more interesting properties of logarithms. If you wanted to know, let's say, the natural log of 1 is equal to 0. Why? Because e to the 0 equals 1. The same thing could be said of log base 10, because 10 to the 0 power equals 1. So that's going to be true for all logs. They'll all cross the axis at 1, 0. Now let's try another one just to see how different it looks. Instead of log x, let's try base 10. Let's see, here it is. They do have that right here. I think you'll see that it looks very, very similar. Yeah, I think you'd be hard pressed to see the difference. This is log base 10. The other one we just had a minute ago was the natural log. The basic shape is always the same. All right, so let's get back to this. So we know what common logs are. We know that natural logs are. The properties. Okay, this is what we were just discussing. The log of, no matter what the base is, the log of 1 is just 0, because any number raised to the 0 power will give us back 1. In general, of course, as you know, x to the 0 power just equals 1. The log to its own base, on the other hand, let's say you have the log base 10 of 10. This equals 1 because 10 to the first equals 10. And that, of course, means that log e also equals 1 because e to the first power equals e. If you're not sure, you can prove that with your calculator. Okay, here's another one. The log of base b of b to the x power is just x. So in other words, this would be the same thing as saying the log to base 10 of 10 cubed is 3. And it should be clear because this is the same thing as log 10 of 1,000, because ten cubed is 1,000. And for the logs, okay, because, well, obviously e to the second is e squared, so we don't, there's nothing you can do with that one, but the logs, so in other words, when you have natural logs, log of e to any power, let's say a is just a. It's almost like you can think of it as the log and the e to the x canceling each other out. Now, this one's interesting. Look at this. If you had 10 to the log 10 of 1,000, this equals 1,000 because this is equivalent to 10 cubed this piece by itself is just 3. And if you have e to the log of, let's say, x, it just equals x. Oh, and up here, let me add one more thing here. So we've got some very interesting properties. Let me try to summarize this a little bit better here. If you jump, let's see. I want to write the log properties separately here, the natural logs, I mean, just because these are the ones we are most likely to encounter. So the two that I mentioned here were that log, e to the x equals x, and e to the log x equals x. Now, we're about to start the properties, the algebraic properties, and you'll see that these can come in very, very handy. They're frequently used to help us solve for much more complicated problems, and you'll see why in a few minutes. The bottom line, though, is that they can take a messy situation and make it a lot simpler. And that's what we would like. We'd like to see when something looks like a mess, if we can simplify it, that certainly makes things a lot nicer for us. All right, here's a good example. The log of a product is the sum of the logs. So just as a couple of quick examples, the log to base 10 of, let's say, 10 times 100. All right, no, hold on. I just want to keep this simple. Could be rewritten as log 10 of 10 plus log 10 of 100. This one is equal to 1 because 10 to the first equals 10. This one equals 2 because 10 squared is 100. Now, in a case like this, you could have solved it directly because here you can see clearly that log 10 of 10 times 100 is 1,000, which you've already seen equals 3 because 10 cubed is 1,000. So we already knew, I mean, you could see that it's 3, but this way you can see that the property does work. And again, it's something that can be very, very useful. Now, if you have natural logs, it also works for them as well. So for example, let's say we had natural log. You could just write it like this. You don't actually need parentheses around these x's and y's. Usually we reserve that for messy expressions. They can be written like this. It means the same thing. All right. Let's see. How about this case? Oh, by the way, naturally enough, this is referred to as the product rule for logarithms. All properties in math have to have a name. This one is known as the product rule for logarithms. Very, very simple and straightforward. So, how about this one? This is another thing that I can do. You see what I've got here? I've got the product already written out. Now we know that this is true because 10 squared is 100. But look what I can do. If it makes things easier for me, I can rewrite this because 10 times 10 is 100. I can also write this as log 10 of 10 plus log 10 of 10. And of course, that didn't help in this case, but sometimes you can break up this product into two easier pieces to help solve for it. So it can go both ways. In other words, the usefulness of this rule can come about in a couple of different ways. Okay. Now, here's another good example because this one shows that this can apply to a product of three terms. It's not just two. In other words, the log of, let's say, x, y, z can be written as the log of x plus the log of y plus the log of z. So there's no limit on how many terms we can turn this into. It works with 3 as well as 2, and it works with 4 and 5 and 6 and all of them. So this is what I mean. Look how easy that is. Now, sometimes, again, this can be very useful for certain types of situations. Like suppose I had something like this. I have the log base 10 of, 1 million. Now, I know that this is 6 because 10 to the 6th equals a million. But what I could have done here is I could have written this as log base 10 of 10 plus log base 10 of 100 plus log base 10 of 1,000, because the product of 10 times 100 times 1,000 is in fact a million. And that means I've got 1 plus 2 plus 3 equals 6. All right, now, if there's a product rule for logs, guess what else there has to be? A quotient rule. And you can probably guess how that's going to work based on what we've seen so far. So if the log of a product is the sum of the logs, the log of the quotient must be the difference of the logs. All right, and that's exactly correct. So let me show that to you right now. So the log of x over y is the same as log x minus log y. Okay, so here's an example. What if, let me just make one up right now. How about this? Now, clearly, I can simplify this and turn it into log 10 of 10, which is just 1. But what I could also have done is this. And of course, I'll get the same result. All right, so how about this one? No matter what the base is, this is the same as the log of the numerator minus the log of the denominator. Now, of course, we can't actually solve these without knowing the values of x and y, but this is what they're equal to. Okay, so you can see that the two are closely related to each other. Now, there's another case which is really helpful, the so-called power rule for logarithms, which is surprising when you first see it. Let's say I have an exponent, the log of an exponent. Look what I can do with it. The log of x to the n power can be rewritten as n times the log of x. So in other words, if I have log 10 of, let's say, 10 to the 5th, this is the same as 5 log 10 of 10, which is 5 times 1, which is just 5. But we could have figured that out separately by noting that log 10 of 10 to the 5th is the same as the log of 100,000, which equals 5 because 10 to the 5th is 100,000. So they clearly must mean the same thing. Or you could say something like this: the log of x to the 4th power equals 4 log x, natural log, that is. The log of e to the 4th would equal 4 log e. Oh, this is something I forgot to mention earlier. Maybe I didn't. The natural log of e is just 1. That's another key property. If you're dealing with natural logs, in fact, let me go back here and add that to my list. I was making up a list of key properties for natural logs. Here's another one that might come in handy. But it makes perfect sense because e and e to the 1 are the same thing. So based on this property, it must be the case that log e must equal 1. I just want to mention that because that's a very useful property. All right, so let's get back to this. So the so-called quotient rule. Let's see, what else do we have here? Oh, here's a good one. By the way, here's where we're trying to kind of demonstrate why this is happening. because now we know from the rule but here's the reason why, because x squared is just x times x. And here we're using the product rule to break this up into two sums, each of which is just simply the log base b of x, so therefore it equals 2 log bx. So there are two reasons why this is true. First, just following the rule, but just noting too that this is the same as log b of x times itself. All right, so anyway, now how about this one? Here's an interesting case. What about the log of a radical? Well, here the key to the whole thing is that the square root of x, of course, as you know, is simply x to the 1/2 power. So therefore, by rewriting it that way, it becomes clear that based on the power rule, this is the same thing as 1/2 log 10 of x. So let's say I had something like this. Well, that's a tricky one because this is nothing but x to the 2/3 power. So that means what I've got here x, sorry, I almost lost the x. Okay. The key to the whole thing is recognizing that this thing is in fact x to the 2/3 power. Then you can use the rule, the power rule, that is. Now look at this one. This is where you can see this one could really come in very handy. This one involves multiple rules. Okay, we're going to sort of tie together a lot of rules that we've been using. Look at this catastrophe. All right, well, I'll give you a minute to catch up, and I'll show you. It's not that scary, but you can see that it needs a little simplification. All right, here we go. Look at this thing. So what I can do is combine the product and the quotient rules first. I've got these two are added together, but then I have to subtract this one. And I'm not done yet because this one, you can see I can now simplify this with the product rule as 4 log x. So this is my final result. Well, you can see I've combined like basically 3 rules here to get to this answer: the product rule, the quotient rule, and the power rule. Now, once I have the information about the actual values of x and y, then I can come up with an actual number. All right. Oh man, there's another one coming that looks pretty scary. All right, let's look at it. So, ooh, look at this one. Now, again, it's really not as bad. In fact, this is kind of what I was just showing you, but log base 10 of radical x, because this is x to the 1/2, it reduces to 1/2 log 10 of x. Down here, the same principle. This is x to the 2/3. I can simply rewrite it as 2/3 log x. I think you'll agree this is simpler to deal with than this. Man, those scary examples just keep coming, don't they? All right, there's one more, and then we're going to look at a very interesting result, which involves the bases of these logarithms. All right, let's take a look at it. Oh, well, these are pretty straightforward, I think. No, but they're all good examples. You can work it both ways. In other words, if you have this, you can turn it back into this. There's no law that says you have to start with an exponent and work it back to this form. Either way, whatever's more convenient, that's always available to you. Here, for example, if I take this and rewrite it as log base 3 of 2 to the 5th, it reduces to log base 3 of 32. And then this one, I can turn this into log base 10 of 100 squared, which is 10,000. And it turns out this is equal to 4, although I could have done this directly by noting that this is just 2 times 2, which is 4. This piece by itself is 2 because 10 squared is 100. All right, now this next result, I think you'll find it very interesting. It turns out that you can change the bases of your logs to a more convenient form with this transformation that I'm about to show you. Now, it's going to look very abstract when you first see it. It'll look a lot easier, or it will be more straightforward when we see actual examples. Okay, so, wow, now that looks pretty frightening when you first encounter it, but you'll see that it can be very, very useful. What's happening here is that I've got log to base b of x. I can rewrite that as the ratio of another base x over b. So how would that work? All right, let me give you a chance to write that down. We'll look at some examples of this and when it might actually come in to be very useful. And then, now the reason why I think you'll find this helpful is especially with your calculator, because it only has one base, two bases to choose from. Okay. So are we ready? By the way, these ends can be anything, literally anything. That's up to you. You can choose the ones that are convenient. And so here's an example of this. if you notice, log base 10 of 100 equals, now here the 2 is completely arbitrary. It can be anything as long as it's the same in the numerator and the denominator. And in fact, you could actually write this as log 100, natural log, over natural log 10. Now, the reason why I wanted to mention that is because now we can confirm this on your calculator, which does not have log to base 2, but it does have the natural log. So in fact, if you, well, first of all, over here, you know that this is equal to 2 because 10 squared is 100, but let's prove it. Why don't we go to our calculator and calculate log 100 and log 10 and prove that this works. So log 100 on your calculator, type 100 natural log x, is approximately 4.60517, let's say, and then log 10 is approximately 2.30259. Now, of course, there's going to be some rounding problems, but if you take that ratio, it's like 1.99999, so you can round it to 2. Now, let me show you why this might be helpful on your calculator, at least, when you've only got 2 logs to choose from, 10 and base 10 and the natural log. Suppose you need something different. Suppose, for example, you need to discover, for some reason you're working on a problem and you need log 981. Now, your calculator does not have log 9. Like I said, it only has log base 10. It has log E or natural log. It doesn't have this. Watch what I can do. If I'm not sure, all I have to do is take the natural log of 81, which is on your calculator, and the natural log of 9. And let's see what that is. The natural log of 81 is approximately equal to 39. 4449, and then log of 9 is approximately equal to 2.197225, and the ratio of those two numbers is almost exactly 2. Now, that should come as no surprise because this is 2 because of the fact that 9 squared is 81. But because if you didn't notice that, if you need a log with a base other than 10 or natural log, you can easily figure it out by using this formula. You can either use base 10 or you can use natural log, it doesn't matter. But this way you can actually, in principle now, solve for every single log. And this is probably why they only gave you the 2 buttons, natural log, log 10, because those are the 2 most commonly used ones. And because now we can see that we can use those 2 to solve for any other log you might encounter in practice. So these guys know what they're doing. There's only so much space on this calculator, and they decided to pick the most important ones, obviously. Okay, now what's coming up next is, with all of this information, we're going to now try to solve what are called exponential and logarithmic functions. Now, we already know what an exponential function is. Exponential simply means x is in the exponent. The logarithmic functions just involve logarithms. So what we're going to do is use the so-called one-to-one property of exponential functions, which is quite handy. There it is. It's kind of, it doesn't look so important, but what it's saying is that if you have two numbers with the same base, they only can equal each other if their exponents are equal. Well, that seems like common sense, but you'd be surprised how helpful that proves to be. All right. So in other words, it's saying, like, for example, 2 squared and 2 squared are the same thing because s equals t. But watch, when you see this next equation, you'll say to yourself, oh no, what am I supposed to do with this one? And then you'll realize this is a very helpful property potentially, because remember, with these exponential functions, we have x's in the, or functions of x in the exponent, which makes things very complicated. So anything you can do to simplify it is going to be very welcome. I think you'll agree. All right, so here's an example of what I mean. Now look at this equation. Before, like an hour ago, what would you have said here? What can I do? I don't understand. How am I supposed to solve for this? But because of that property, remember, b to the s equals b to the t only if s equals t. So this implies that because they have the same base, those exponents are equal to each other. And look how nicely this reduces. Suddenly, all we have is a very simple x minus 1 equals 2x minus 4, which we can just solve the normal way by rearranging everything algebraically. And we end up with 3, x equals 3. Okay, so let me show you that on the next page. Oh, what a relief. So you can see here's an example of when a potentially horrendous equation can be reduced to something much simpler through the use of exponents and logarithms. Now we can double check that. Let's go back to the original equation, and then let's plug in 3 and see if this makes it work. So I plugged in 3 for the x's, and in fact, yes. Okay, so it looks like it worked. Nice. All right, so let's look at another one. This one's a little different because we have to do some careful thinking first. What about this one? If you looked at it initially, you'd say, oh my God, what am I supposed to do here? But if you look at it carefully, you'll see, number one, that 256 is 2 to the 8th power. But still we have the different bases. But, or do we? Because remember, 4 is 2 squared. So therefore, 4 to the x minus 5 equals 2 to the 2x minus 5. Okay, that's the challenge here. So therefore, what we have here is 2 to the 8th equals 2 to the 2 times x minus 5. Now we can set these equal to each other and solve for x. You see how that works? That was very clever. Okay, and then of course now we have to solve for, now we're going to set 8 equal to 2 times x minus 5, which of course could also, if we want to, we can simplify this a little and write it as 2 to the 8th equals 2 to the 2x minus 5. And now these are just set equal to each other. 8 equals 2x minus 5. A 10, sorry, that's 10, my fault. That's a 10. And then we'll solve for x. All right, so when we set these equal to each other, then we'll of course end up with 9. And so if we go back to our original equation, where it said 256 equals 4 to the x minus 5 power, we can double check now. And then we can just say that, is it true that 4 to the 4th is 256? Yes, it is. Okay, so you can see this started out as a very scary looking formula, but it turned out that it wasn't. But we had to recognize this for the type of problem that it is. And that meant rearranging it a little bit to come up with a common base. Without the common base, we can't do any of this. So that was the challenge. This was the really tricky part right here, I think. Recognizing that that means that 4 to the x minus 5 is the same as 2 to the 2 times x minus 5 power. Okay. So, all right, since, it's after 9:30. All right, so we're going to carry on with some more algebraic manipulations here and to help us solve some problems. But first, why don't we have our break? And then we'll carry on. We got some scary stuff coming up here. And so we'll need to have a little break before we deal with these problems. And then we'll be ready for chapter 5, which is something that you've seen before, but it's probably been a while. And you probably could stand some review anyways. So we'll hang on to that till after the break, and we'll take it from there. How about that? All right. All right. I'll see you in a bit. Okay, let's do this. All right, so let's see. Now, we can certainly use, this section is called using like bases to solve exponential equations. So of course, this is going to involve rearranging an exponential equation so that we can take advantage of these properties, but we have to make sure that they have a common base. So here's some quick examples. And really what it shows you here is that if we use our ingenuity a little bit, we can often take an equation that does not look very promising and turn it into something which is easy to solve. Like, look at this. You might look at it and say, oh boy, what are we supposed to do with this one? But algebraically, you might recall that dividing by 3 is the same thing as multiplying by 3 to the minus 1 power. And also, whenever you have a situation like this, x to the n power times x to the m power, then you end up with x to the n plus m power. So here, what I can simply do is consolidate or add these two. And now all of a sudden, I have 3 to the 4x minus 7 power equals 3 to the 2x minus 1 power. And based on the rule we had earlier, where we saw that when we have a common base, the one-to-one property guarantees us that these exponents must be equal to each other. So we set them together to equal to each other. So in other words, we're setting 4x minus 7 equal to 2x minus 1, and then we simply algebraically solve for x. And we end up with x equals 3. Now, let's just double check that. Let's go back to the original equation. 3 to the 4x minus 7 equals 3 to the 2x power over 3. So let's substitute 3 for all these x's. So that means we'll have 3. This is 12 minus 7, which is 5. Okay, and then the final result is that 3 to the 5th equals 3 to the 5th. And that means we've done this correctly. All right, so that worked out pretty well. But again, you may have to do a little rearranging algebraically to take advantage of this property, but in many cases, it's not that difficult. Now, how about this? Now, in more general terms, solving exponential equations can be done by applying logarithms to them. So let's take a look at this example. Now here, you can see we do not have the common base that we need. So what can we do instead? This looks like a disaster waiting to happen. So just like in many other algebraic situations, if we do the same thing to both sides of an equation, we do not affect the results. So in other words, if I have 3x equals 7, I can feel free to multiply both sides, divide, raise them to their different power. As long as I do the same thing to both sides, I'll end up with the same results. The same thing is true here, except that now I'm going to do something a little different. I'm going to take the natural log of both sides of this equation. So in other words, I can certainly go ahead and do exactly that, and I will not change the equation. But the question is now, why am I doing this? What is this getting me? How is this helping me solve this equation? Well, let's see how this works. All right, so based on the properties of logs that we've been seeing here, we start, and this is what we just did. We took the log of both sides. Now remember, log x to the a power equals a log x. This is our power rule for logs. And the same thing, of course, is true on the left-hand side. So now here's what we can do. why don't we break this up into two pieces? In other words, now I have x times log 5 plus 2 log 5 equals x log 4. And what I'm going to do is try to get similar logs together whenever possible. Now, what do I mean by that? Here I've got x times a log. So why don't I subtract this from both sides? Oh, I just realized there's a problem here, isn't there? Yeah, this is a typo. This should have been negative. Okay, so that's wrong. I hope that God, I hope I didn't mess up the whole thing. Yeah, oh boy. I'll have to fix this and send you out the corrected version. Yeah, I just realized because what happened here was the intention was to, starting with this equation, I had to subtract 2 log 5 from both sides. And this one I got the negative sign. This is not correct. So I'll fix that as we go along. All right, so hold on. Okay, so unfortunately, we're going to get the wrong answer, but you'll see, I'll fix it as we go along, and you'll see how it's supposed to work. So this is meant to be negative. This is negative. This is negative. But over here on the left-hand side, look what we're able to do. We can factor out x log 5 minus x log 4. And again, these parentheses are not absolutely necessary. X log 5 minus x log 4 can be rewritten as x times log 5 minus log 4. Okay, and then that in turn can be written as x log 5 over 4 due to the quotient rule of logarithms. And so that's what I've got here. On this side, we have what's supposed to be a negative log 2 log 5. And then we can just simply divide both sides by this term because it's a constant. And I'm going to wind up with this result. Now, of course, this is supposed to be negative. Okay, so those all should have been negatives. I'll fix those and post the corrected version between now and next week, let's say, or next time we meet. But anyway, so what ended up happening though was we started at the beginning, we were hoping to use our one-to-one rule, and we realized that that wasn't likely to happen. Oh, okay, yeah. If your Wi-Fi is screwing up, just log back in. That's okay. It happens surprisingly often. You'd think that this only happens once in a while. This happens to me quite a bit during these classes. People are having issues with their Wi-Fi. It's just the Wi-Fi just is not nearly as reliable as people seem to think it is. It really isn't. But anyway, so we started out with this problem that looked like it was not going to be solvable because we do not really have any way of creating a common base. But it ended up not mattering because we took the step of taking the natural log of both sides of this equation, and then with a little algebraic rearrangement and applications of the rules, we discovered that it was not difficult at all to come up with the final answer. Although it's a very messy answer, it is the right answer. Okay, it is after I put in the negative sign. Okay, what else can we do here? Sometimes we can solve these equations just by directly applying the logarithmic properties. Okay, so remember, let's go back and revisit them for a second. We know that, oops, hold on. Here we go. We start out with the product rule. In fact, you know what? Why don't we do this? Why don't I just copy these onto a single sheet or slide so we can have them all together in one place. I like that. I like the idea of having them all together. It's just so much more convenient. So let's do that right here. Okay, so there's the product rule. And then we had a quotient rule as well. Let's go grab that one. Oh, almost. Here it is. This is our quotient rule, as we called it. And then finally, we need the power rule. Okay, so they're all together now, one convenient location. So now we have we'll call them logarithmic rules. And now we can proceed to use these with our equations to come up with the correct answers. Okay, so here's a good one. Let's say we have these two, they have the same base. And so here we're simply combining them. We're essentially factoring them out. Okay, so in other words, if you have log 2 of 2 plus log 2 of 3x minus 5, remember, this is the equivalent of log 2 of x plus log 2 of y, which, as we know from this property, is the same as log 2 of xy. So what we're going to do here is consolidate these into a single term where I multiply x by 3x minus 5. Or, of course, that means 6x minus 10 equals 3. So now what do we do? Well, it turns out, now you remember, because of the way logs are defined, if you have the log to base b of, let's say, 10 to the a power, this is a. In other words, in this case, what this implies is that 2 to the third power equals 6x minus 10. These both mean the same thing. Okay, so in other words, if you forget, just use a simple example. Log 10 of 1,000 equals 3, because 10 cubed is 1,000. And you're doing the same exact same thing here. You're taking the base, raising it to this exponent, and setting it equal to what's in parentheses. So 2 cubed is, in fact, 6x minus 10. And now we can solve this very easily because 2 to the third power is just 8. So 8 equals 6x minus 10, which means that, of course, you add 10 to both sides, divide by 6, and we do eventually end up with 3. And again, we can double check this. Log 2 of 2 plus log 2 of 3x minus 5 equals 3. That was the original equation. Oops, sorry, that's log 2 base 2 of 2 plus see, log 2 of 3 times, remember x is supposed to be 3 here.
What did you say? ¿Tú te quieres ganar una galleta o un trompón? ¿Ah? ¿A qué, miss? No.
Okay, so then we have log 2. This is 4. Okay, So now, is this true or isn't it? Well, remember, log 2 of 2 equals 1, because what you're actually seeing here is that log 2 of 2 to the 1 is 1, because 2 to the first equals 2, and then log 2 of 4 equals 2, because 2 squared equals 4. So what you're seeing here is 1 plus 2 equals 3, and 3 equals 3. So we must have done it correctly then. All right, but the bottom line here is that you're able to get this by consolidating these two logs based on this multiplication or product rule, they call it. And once you got it to that point, though, you still needed to rewrite this in terms of an exponent. So there's this logarithm implies that 2 cubed is equal to 6x minus 10. Without that, you would not have been able to solve this. So this is not just even one of the rules. This is actually coming from the definition of logarithms themselves. Okay, so that's where this came from. Now here's one that you can use. 2 log x plus 3 equals 7. 2 log x equals 4. Now I divide both sides by 2. Now what are we supposed to do with this one? Okay, well, you might recall that 2 of the other properties we saw that are unique to natural logs were that the natural log of e to the x is just equal to x. E to the log of x equals x. How does that help us? Because look what I can do now. And I did say before that with any algebraic equation like this, you can do any algebraic operation to both sides of the equation without changing the results. So look what I can do here. And again, the reason why that's helpful is because this simply reduces to e squared, and e squared is a constant. You can leave it like that, or you can figure it out on your calculator as approximately 7.389. All right, and that's your final answer. Or, of course, you can leave it like that, and if you want to double check, you would have 2 natural log of e squared plus 3 equals 7. The natural log of e squared is just 2 based on this property, and then you have 3, and so you end up with 7 equals 7. All right. Anyway, look at this one. 2 log 6 equals 7. So of course I divide both sides by 2. And I'll use the same trick. I'll raise both sides to the e raised to that power. So I'll have e log 6x equals e to the 7/2. And again, remember, e to the log x equals x. Okay, so therefore e to the log 6x must equal 6x. That equals now e to the 7/2. And I can just say x equals 1/6 of e to the 7/2 power. And I can just leave it like that. And if you want to plug it in and double check, you can certainly feel free to do so. Okay, now we've got another one-to-one property here. In fact, why don't we do this? Once again, let's put these together in one convenient location. Remember we had the one-to-one exponent properties. When we first started out, let's take a look at it. Let's go, I'm just going to go grab it again. Because now you can see how they correspond to each other. In other words, we're going to be able to do this with both exponents and logarithms. So way back here, we had this one-to-one property. Okay, where is it? There it is. Okay, that's for exponents. There's an equivalent version for logarithms. Let's see what that one is. And it's very similar. I mean, you get the idea. All right, just to be consistent, I'll change these all to lowercase. Not that it really matters, but I just, they should all be the same. All right, so what this is saying is that now with logs, these two logs will only equal each other because they have the same base. They can only equal each other, of course, if s equals t. So how does that help us? Well, let's look at this one. Log 2, 3x minus 2 equals minus log 2 of 2 equals log 2x plus 4. So we'll combine these. We'll use the quotient rule over here to rewrite this. Remember, log with any base of x over y equals log of the same base of x minus log base of y. All right. And then on the right-hand side, we leave it the way it is. But now we have the same base. So we know that these two have to equal each other. So we can just set them directly to each other. 3x over minus x over 2 must equal x plus 4. And then algebraically, we double both sides. We multiply out this expression. We subtract x from both sides, add the 2. And then we end up with our final result, which is x equals 10. And if we feel like double checking, this is going to take up a lot of space. All right, what the heck? Let's throw it in there. So that means log 2 of, now this would be 30 minus 2, 28, minus log 2 of 2 equals log 2 of 14. But because of the quotient rule, we have log 2 of 28 over 2 equals log 2 of 14, and we're done. Log 2 of 14 does, of course, equal log 2 of 14. All right, so logarithms are a very commonly used concept that can help us greatly when solving for very complex equations, as are exponents. So, these are, like I did say, I think once before, the chapter 4, you run into this a lot in practice. These concepts are really, really useful. So now, though, we're going to switch into something which is a little bit more specialized. Something you've seen before, but it's probably been a while. Unlike what we did here, what we're about to look at really is more useful for certain disciplines like physics, let's say, or physical sciences. We don't run into this very often in, let's say, business or other more applied areas, but it's something that's important to be comfortable with. So what in the world am I referring to here? That would be Trigonometry. That's right. How long has it been since you thought about sines and cosines? Well, guess what? They're coming back to town for a visit, and here they are again. Now, you might recall that the basic 6 trig functions were sine, cosine, tangent, cotangent, secant, and cosecant. We need to start out with these. We need to, first of all, remember what they mean and how they're defined. Now, in order to do that, we need to draw an angle. So an angle is the relationship between two what we call rays. Now, you might remember what separates a ray from a straight line is that a straight line goes on forever in both directions. A ray has a specific starting point, but it does go on forever after that. Okay, so line would continue on forever. A ray has a very specific starting point, but then it goes on forever. The angle theta is the relationship between, or it shows you how closely connected the two rays are. Now, so there's our Greek letter theta, which represents angles. Yes, that's right. So I see somebody has remembered a mnemonic device to help us remember all of our trig functions. And so since we remember, we may as well go over it right now. Let's say we have a right triangle, just to keep it simple, although it doesn't have to be. All right, here we go. Now, this is the symbol that we have used. You may have seen this before. This means that this is a right angle, which is 90 degrees. The sides of this triangle are perpendicular to each other. This is therefore referred to as a right triangle. And you'll also recall that all the angles in a triangle have to add up to 180 degrees. So now it's possible. Now in this case, if I've drawn it correctly, this could be 45 degrees, although it doesn't have to work out this way. And so we'll call this side A, side B, and side C. And of course, side C has a special name. Who remembers it? What is the name of this side of the triangle? I'll give you a hint. It starts with an H. Hypotenuse. That's exactly right. Now, you'll recall, let's just one more blast from your past, the Pythagorean theorem, which ties together the lengths of these sides for a right triangle. What was the Pythagorean theorem? That's right. So the Pythagorean theorem tells us a squared plus b squared equals c squared. And you might recall that there were certain ones that you may have been asked to memorize. For example, why is this the case? Because 1 squared plus 2 squared. Oh, wait a minute. No, sorry, I screwed that one up, didn't I? It would have been, it's been a while. Yeah, it would have had to be this way. There we go. So we would call that a 1, 2, radical 3 right triangle. Remember this? There are a handful of combinations that you might have been asked to memorize. 1, 2, radical 3, for example. How about this one? One radical 2. This is the case when you have 45-degree angles. There's another one that I remember, a surprising one. Um, 5. Yeah, that one, surprisingly enough, is also one of the ones you might have remembered. 5, 12, 13. No, maybe not. It doesn't matter anymore. What we're interested in here is something a little bit different. So what are we going to do here? Let's take a look at a triangle, which, by the way, this does not only apply to right triangles, but it's easier to illustrate it this way. Suppose I have angles, I'll call them A, B, and C. How about that? So you might recall, and this is the mnemonic, and I remember I said before, sometimes mnemonics help and sometimes they don't. I found that this one was particularly helpful for some reason. It just stuck in my memory. What exactly is this all about? Well, it's a simple way of saying that the sine equals the opposite over the hypotenuse. Oh, therefore the O and the H. Okay, O and H. Ka means the cosine is the adjacent over the hypotenuse. AH, get it? And then tangent equals opposite over adjacent. Okay, so those are the first three. The sine, cosine, and tangent can be memorized with the SOHCAHTOA formula. Now, what about the rest? Remember I mentioned up in the front, there are actually 6 altogether that you need to know. Cotangent, secant, and cosecant. Well, I don't think there is a mnemonic device for these 3. I think you just have to remember them. So how does that work? So cotangent is 1 over the tangent. So in other words, it's A over O. Remember, if the tangent is opposite over adjacent, the cotangent must be the inverse of that. Secant is 1 over the cosine, which means that it's H over A. And then cosecant is 1 over the sine, which implies that it must be H over O. So I don't believe anyone's ever come up with a mnemonic for these guys. So I think you just have to memorize them. It's too bad. The SOHCAHTOA works very nicely, but you just have to remember them. So this is how these functions are formally defined on angles in a triangle. Oh, okay. They save those for the end of the run. I didn't, yeah, because when they first teach you about trig, they often just show you the sine, the cosine, and and the tangent. They often don't tell you until later on that there also exists the cotangent and the secant and the cosecant. So I'm not surprised to hear that. Yeah, it depends, and it depends on who's teaching it. So anyway, so hopefully this is all stuff you've seen before. It's okay if you've never seen it before. It'll just make a little bit more sense if this is something you've done in the past. So now just a little bit more of terminology here. I just want to mention here before we go any further. Here's a diagram that we should be comfortable with. This is a triangle. Obviously, this is an angle of some kind. And so here we have the angle theta. And there's what we call an initial side, and there is a terminal side. And the vertex is where they come together. So what they're trying to illustrate here is that if you can imagine on the XY coordinate system, we're moving in this direction. And so we have an initial side, a terminal side, which indicates that we start here. They could have just as easily called this a starting side and a finishing side or something like that, if that's what you want to think about. But that's what these are supposed to represent. And then the vertex is the point where they meet. All right, this is just terminology. We don't have to worry that much about it, but when you run into these terms, you do need to know what they're referring to. So basically, you can think of the angle as the rotation. Now, by the way, you might remember that within a circle, let's just quickly review this. We know that a triangle has altogether 180 degrees in it. A circle, though, contains 360 degrees. So if you were to start, let's say you look at the XY coordinate system, and this is, of course, X and Y. These are the four quadrants. The distance from the x-axis to the y-axis is 90 degrees. And then again, from here to here is 90. And then we have 90 again. And then finally, 90. So altogether, this adds up to 360 degrees. Now, you might ask yourself, you may have asked yourself in high school, why do we have to do everything in terms of 60s? Why do we have such peculiar numbers? It's because the Babylonians' numbering system was based on 60, and that's why we wind up with these strange-looking numbers. You know, it would be nice if they were all 10s and 100s, but it just didn't work out that way. So this is what we're stuck with. So a single degree could be thought of as 1/360th of a full rotation around a circle. Yeah, I mean, it's kind of a strange, I mean, everybody kind of intuitively knows what a degree is. It's a very small amount because the full circle is 360. Now, if you've ever studied, well, let's see. If you've ever owned a compass, what is a compass? Does anyone know? It's an ancient device that does what? Well, it contains magnets, but what is it designed to do? All right, I'm going to draw a little picture, not a very good one. Yes, that's exactly right. It's pointing, it's a little magnetic thing, and it's showing you where you are relative to north. It's pointing towards what we call magnetic north. This is why they call it that. By the way, if you recall, the Earth itself is divided up into degrees in the same way. The Earth is sort of a big circle. Not really, it's kind of a sphere, but it's a circle. We think of it as a circle. And you might recall that going north and south, we have a measure called latitude. And the latitude is measured in degrees relative to the equator. In fact, this line here is supposed to be the equator. So in New York right now, we're roughly at about 42 degrees north. I mean, we could double check that. Roughly, you can, believe it or not, you can go to Google and say, what is our latitude? Okay, what is the latitude? Oh, there you go, 41. All right, 41 north. This western measure is different though. 41 north. I'll get to that in a second. Whoops, 41 degrees north. The equator is 0. Okay, so if you were to look at, for example, what is the latitude of Rio? It's 22 south. It's going in the opposite direction. There's no such thing as a negative angle here. It goes to south. Now, the North Pole would therefore be 90 degrees. Let's check that. Let's confirm that. 90 degrees north. By definition, the latitude of the North Pole is 90. And then, of course, the South Pole down here would be 90 degrees south. Okay. So if you ask for, let's say, the latitude of Antarctica, it's almost all the way down, roughly 82.86 degrees south. It's almost exactly on the South Pole. Okay, so that's latitude. Now, by the way, if you look at this very carefully, the numbers actually go past 82. Let's go back to Purchas for a second. .0400. Now, what happens here with these degrees, they're not quite precise enough for many applications, so they're further subdivided, believe it or not. Latitude is divided into degrees, minutes, and seconds. Okay, so 1 degree equals 60 minutes, and then 1 minute equals 60 seconds. Okay, so when they write it like this, I'm not quite sure. I have to double check that. How we're supposed to read this. Okay, well, see here what they've done is they've broken up. It's 41 degrees, 56 minutes, and 54.3732 seconds. Okay, so that's what that's supposed to represent. And if you notice the symbols that they use, which are pretty cool, degrees are measured. The symbol for degrees is this little circle. Minutes are expressed with that little single apostrophe, I guess you could call it. And then seconds are represented with I guess you could call it double apostrophes. I'm not sure if there's a proper name for that symbol or not, but so if you're a navigator, if you're on a ship out in the middle of the ocean, you need to know this stuff, but like the back of your hand. Okay, you need to know precisely where you are. And since you're out in the middle of the water, you're not going by normal mileage, you're going by minutes, degrees, and seconds relative to the equator. Now, in addition to north and south, we also need to know what direction we're heading, going from west to east. So going in this direction, instead of latitude, what do we have instead? Does anyone know what that is? What is the measurement that goes from east and west? It's called longitude. That's right. That goes from east to west. Now, interestingly enough, latitude, sailors have been able to measure latitude for centuries because it only requires us to observe the angle of the sun. Longitude is a completely different matter. Longitude requires us to know precisely what time it is. So it took a very long time for sailors to be able to measure longitude. In fact, it wasn't really discovered how to measure it properly until the very late 18th century. And only then because the King of England offered a prize to whoever could come up with the best way of measuring longitude. It was that important, and yet it eluded them for many, many centuries how to do this properly. Anyway, now here's my question to you. You know that the equator is the line of zero latitude. What is the equivalent version for longitude? In other words, where is 0 degrees longitude? What is the equivalent of the equator going north and south? What is the name of this line? Oh, it's been too long. Here we go. Oh, somebody's got it. It does have something to do with Greenwich Mean Time. That's right. It's called the Prime Meridian, and it goes through Greenwich, England. Now, why Greenwich, England? Because what's located there is the Royal Observatory, which was set up by Sir Isaac Newton. And he was the one who came up with this idea of longitude. So naturally enough, the zero longitude is in Greenwich, England. It goes through the Royal Observatory. And in fact, I've actually been there to see this. There's actually this enormous red, if you're walking around in that area, there's this enormous big red stripe that they put into the ground. Okay, where did they put it? That's the observatory. Oh, here it is. Here it is. You can see right there. You see that line right there? That is the prime meridian. And so everybody who goes to Greenwich as a tourist, like I did, gets their picture taken standing with one foot on either side of it, because that means you're simultaneously in the east and in the west. It's pretty cool. It's fun. It's just like when you go to London, everybody has to walk across Abbey Road and get their picture taken walking across Abbey Road. It's the same thing. Everybody has to do it. The observatory is up here. It was set up by Sir Isaac Newton, in honor, I shouldn't have said that, in honor of Sir Isaac Newton, who came up with this idea. And this is where this is where the prime meridian is located in Greenwich. So anyway, all that fun stuff is just designed to remind you how angles work. And you can see angles are set up for many applications in the real world. But if you, getting back to the compass will show you where you are relative to what's called magnetic north. Now, the unfortunate reality of the Earth is that the North Pole, the Earth has two magnetic poles, north and south, but they're not precisely lined up with longitude and latitude. It's off a little bit. In fact, let's go see if we can find out how far off it really is. What is the longitude? I guess I should say it's not the latitude that's off, it's the longitude. How far is magnetic north from true north? All right, 1,200 miles. Okay, so it's off a bit. So your compass is not pointing to 0 degrees, I mean exact north, but it is pointing to what we call, here it is. Here's a perfect example. This is the true North Pole, 0 degrees latitude and longitude. This is where the magnetic North Pole is. So your compass is pointing here rather than here. Okay, but the true North Pole is both 0 longitude and latitude. Okay, no, sorry, it's 0 longitude, but 90 degrees north latitude. That's right. But so the compass is pointing a little bit off, but it's close enough that you can find where you're going. How do you like that? Interesting. So you would have probably discussed all of this in high school. It's just a little bit of, you know, I guess we're sort of enjoying our memories of this wonderful knowledge we learned in high school. We're reminiscing about the past here. But yes, so angles are set up to work this way. A full circle is 360 degrees, and all the rest is taken from there. All right, anyway, enough of that fun stuff. So a standard angle, or an angle is in a standard position if its vertex is the origin by which we mean the point where both x and y are equal to 0. So we always assume that we're going clockwise. Okay, clockwise. And since we're talking about history here, why is that direction clockwise, not the other way? Okay, so we're moving clockwise here. So the reason why that direction is considered to be clockwise is very simply, it wasn't just randomly chosen, because how do we tell time with a sundial? We look at the shadow. And what direction does that shadow move as the day evolves? It goes in this direction in the northern hemisphere where sundials were invented. Okay, this is the direction that the shadow goes. And so when clocks were first invented, it stood to reason that they would have continued to make the minute hands and the hour hands move in the same direction as the sundials. Because this is, sorry, I'm going the wrong way. This way, this is the direction, because this is what people were used to. So when clocks were first built, they made sure that the hands moved in a clockwise, or they called it clockwise, to indicate this is the direction that the sun moves in the northern hemisphere. In the southern hemisphere, it's the other way around. Okay, so that's where that term clockwise actually comes from. The hands are going in this direction because they follow the path followed by the sun in the northern hemisphere. So that means, oh, what did I do here? I wrote this backwards, didn't I? This is counterclockwise then. My fault. This is counterclockwise. God. Yes, clockwise, as you, of course, goes this way. Although with digital clocks, eventually the term will lose its meaning. Clockwise means the hands go in this direction. Counterclockwise is this direction. All right, now that's down to whoever invented the XY coordinate system, why this direction was chosen. But as far as the actual clocks themselves, they were meant to replicate what was happening with sundials. Okay, how cool is that? Look at that. And you can tell if you look at it carefully, if you set it up properly, theoretically, you should be able to set it up so it can tell you not just the time, but what part of the year it is. If you look at it very carefully, it should be able to do both. Because, you know, the angle will be different at different times of the year. It's going in the same direction, but the angle itself will depend on what time of the year it is, whether it's the spring or the fall or whatever the case may be. Man, that is so cool. Now, you know what that means, though? The next time we go to Symbolab, we're going to see ads for sundials. In fact, why don't we investigate this right now? Just for the fun of it, let's go to Symbolab and ask it to calculate the sine of 90 degrees or something like that. One. Okay. Oh, no, it's still on coins. Okay. I guess it'll take a while to catch up and start showing me ads for sundials. But yes, so you might remember there were several standard angles that you were probably asked to memorize. Usually it would be 0, 30, 60, and 90 to memorize those. And so we'll be going over that again. We're going to see how and why you don't really need to memorize those, but there's a diagram that will help us remember how these numbers actually work. Okay, now, so for example, 90 degrees is considered to be this because we're moving 1/4 of the way around the circle with our initial side on the x-axis and our terminal side on the vertical axis. This is how we formally define 90 degrees. Okay, and you can see, of course, that right here with the vertexes at the origin, the two rays are perpendicular to each other. Now, on the other hand, you can actually have negative angles, if you can believe it, but the negative angles always have an equivalent positive angle. And here's why. Because if you notice, we're going clockwise here. So going clockwise in this direction, 135 degrees, by the way, what it means is 90 degrees for this quadrant, and then halfway through the next quadrant, half of 90 is 45. But if you had gone this way in the counterclockwise direction, this would have given us 225 degrees. Okay, in other words, 180 brings us to here, and then this is halfway through the third quadrant. So these two angles actually mean the same thing. It's just that in one case, we're moving in a counterclockwise direction, and the other case, we're moving in the clockwise direction. So these actually mean the same thing. We're still going to wind up at the same place. All right. So up here, we have 180 degrees. To get us to the other side here. And then this is another 45. So yes, you can have negative angles, but it's just a perspective thing. Which direction are you going in? So altogether, the important ones to remember are 90, 180, 270, and 360, because they represent moving through an entire quadrant or 1/4 of the way through the circle. Okay, so just as a quick review, this is 0. This is what we mean by 0. Right here, you're just right on the x-axis. 90 means you've moved to the vertical axis here. And these are, by the way, remember the quadrants are 1, 2, 3, and 4. They're going in a counterclockwise direction. Again, I don't know why it was chosen that way. It may be that this was invented before clocks came along. That might be an interesting research project, but this is how the quadrants have traditionally been numbered. 180 means you've gone through two quadrants. 270 means you come all the way down through the three quadrants. And then if you go all the way around, 0 and 360 actually mean the same thing. Okay, so, and that implies that this one could also be thought of as 450 because it means you've gone all the way around once plus one more quadrant. And that means that this one is equal to 540 because it means you've gone through the whole circle once plus two more quadrants. And then this one is equivalent to 630. So they mean the same thing. So there's multiple ways, as you can see, of expressing each of these angles. It has the potential to be very confusing, but it's important that we understand what these numbers mean. Man, is this all coming back in a big flood? Is this something you hoped you'd never see again, but now all of a sudden here it is again? That's right. You thought you were done with this stuff, but you were wrong. Okay, you were disappointed. You're like, oh no, not again. I thought we were through with this stuff. All right, now we've got some more key terms here to look at before we can actually start calculating anything. The four angles you just saw here, 0, 90, 180, 270, 360, have a special name in math. They're called quadrantal or quadrantal angles. You don't have to memorize that. You should just, but if you see that word, you should know what it means. Yeah, that's right. Quadrantal angles. Just try to imagine yourself having a conversation and this word pops up in your conversation. Yeah, you know, I noticed some quadrantal angles walking down the hallway here. That would be very strange. Okay, now here's something you might not have thought about in many years. We're all comfortable with degrees, but we also have this equivalent measure, which is called radians. Oh my God, it's been so long. Radians. And the way this works is that 2 pi radians equals 360 degrees. Now, for some applications, it's more convenient to work with radians. It's just like when you stop and think about it, it's really no different than looking at the relationship between Fahrenheit and Celsius. It means the same thing. They're just different units. And of course, we are cursed forever with the Fahrenheit system. We'll probably never get rid of it. The English system itself, you know, there have been a few attempts to get the metric system in the US, but they always failed. So I guess we're stuck with it forever. We're never going to get it. We're stuck with the English system forever. But here, this is different because we pick the one that's more convenient, depending on what we're trying to do. So if you want an exact numerical value, each radian is equivalent to roughly 57.3 degrees. In other words, 1 radian would be, let's say, maybe about here. All right, and don't forget too, you can feel free to write this with the little symbol. We probably won't be writing out anything in terms of minutes and seconds, although we certainly could. You can, for example, write 362.1 degrees, but just be aware that you can always convert them into minutes and seconds, just like navigators do. Okay, and of course our old friend pi, you know, roughly 3.141 ... All right, so let me show you a little chart that will help you, I hope. These are the more standard ones you might run into. These are different conversions between degrees and radians. Now, if you're not going into engineering or something like that, it's possible that you'll never need to think about radians again. But degrees, I think you're more likely to run into degrees, especially like I said, if you're looking at latitude and longitude, you're not going to see them measured in radians. They're always going to be measured in terms of degrees, relative to the equator and relative to the prime meridian. So in other words, now where did this come from? Well, you can see pretty clearly that in order to get from 2 pi radians to pi over 6, that means what we would have done was if we took 2 pi and divided by 12, that's pi over 6 radians. And if you did the same thing with degrees, that would give you 30 degrees. All right. Then for some of the other ones, like 3 pi radians, 3 pi over 4 radians would be easy to calculate. If you always use pi radians as 180 degrees as your starting point, you can find any conversion you want. So in other words, 3/4 of 3 pi over 4 radians would be 3 times 180 degrees over 4, or 135 degrees. They both mean the same thing. Just like with Celsius and Fahrenheit. 0 degrees Celsius, 32 degrees Fahrenheit, they mean the same thing. In fact, you might remember from high school physics, there's actually a third temperature measurement that you may have encountered. So let's say the freezing point of water is Celsius 0, Fahrenheit 32. There's a third scale, which you might recall. Who remembers what it was called? Anybody remember that? Think of high school physics. Oh, I think somebody has it. Kelvin, that's right. Somebody out there has an exceptional memory. Elijah, you have an excellent memory. K for Kelvin. And the freezing point of water in Kelvin is 273. Now, why is Kelvin important? Kelvin, remember, we were learning about it the same time you were learning about, I guess, atoms, because with the Kelvin scale, 0 means absolute 0, which is when atoms freeze. And so, yeah, that's a pretty low temperature. But anyway, now, coterminal angles. We already had this conversation, basically. These are angles that actually, while they have numerically different values, they actually represent the same thing. And again, we explain why, because really these two angles, it's hard to believe, but they're the same thing, because here we're moving in the counterclockwise direction. So you're going 90 degrees to get through the first quadrant, and then another 50 degrees in this direction, whereas down here, you went through 180 degrees to get into the third quadrant, and then another 40 degrees here. So these mean the same thing. We just arrived there from different directions, and these are referred to as coterminal angles. And here's why, because remember, we defined in the beginning, these rays have a special name. The one that you started out with, let's go back here, is called the initial side, and that's true for both of these. And this is what we call the terminal side. So both of these angles have the same initial and terminal side. Coterminal means they have the same terminal side. That's all they mean. And of course, that means they are equivalent to each other. Okay, now a reference angle, oh, by the way, there's some more terminology you may have forgotten. Let's review this real fast. Let's throw this in here. So much terminology here. So there's some angles you might want to remember. An acute angle is less than 90 degrees. Let's just review that real fast. Of course, a right angle is exactly 90 degrees. Oh man, is this all coming back? By the way, I just want to mention in passing, this is the only chapter in the book that we will actually use trigonometry. We're sort of like, we're looking at it because it might pop up again later on, but this is it. After this, no more trigonometry. This is, one time only. After that, we'll be doing completely different topics. So if you don't like this stuff, that's okay, because, we're only going to need it once for this chapter, and that's it, no more. And then after that, obtuse angles is more than 90 degrees. I guess that's all of them. Let's see. Obtuse is more than 90. There's also, I thought there might have been some others. Okay, here's a couple. Complementary angle. Oh, that's right. I think supplementary angles. There's another one called supplementary angles, which adds up to 180. Yeah, there it is. 180. Ooh. Okay. Wow. Remember all this good stuff? Yes, you do. All right. So let's get that in there, just so you don't have to constantly, if you run into these terms, you'll not be constantly wondering what they're talking about. All right, well, you got those out of the way. God, were there more? I don't think so. No, I think that was pretty much it. Never heard of a reflex angle. Huh. All right, well, anyway, let's carry on. Now, a reference angle. Oh, okay. What this is now, before, remember we mentioned that with that diagram, that there's many different degrees that mean the same thing. For example, 90 and 450 mean the same thing, but it goes past that. In other words, every, let me just throw this in here so you can see what I mean. 90 degrees. I wonder if the keyboard has that symbol, the little degrees circle. Hold on one second. It's probably here somewhere. It's OOBO. Why, there it is right there. Yeah, how do you like that? 90 degrees equals 450 degrees because we add 360 to it. But if we keep adding 360s, This one equals a 10 degrees, which equals 1170 degrees. You can see what's going on here. And so I just want to mention that in passing. So this way, when you see this definition, reference angle, it is the smallest acute angle that can be formed from the terminal side and the horizontal axis. So in other words, what if I asked you to calculate or describe a 740-degree angle? It turns out that 20, 380, and 740 all mean the same thing, because to get from 20 to 380, I'm just adding 360. And then I add it again and get 740. So all of these are the same angle. And we say that the reference angle is 20 degrees. Okay. So in other words, that would represent, let's say maybe here. And because the others are equivalent to it, if you go around the circle again, you'll come back to 380. And if you go around again, you'll get to 740, and you keep going on and on and on. All of these have the same reference angle, which is 20 degrees. This is what uniquely characterizes these angles. So in other words, given that there's so many that are equivalent to 20, we need to know what the starting point is, and that would be this 20. They're all derived from this reference angle, which is 20 degrees. All right, man, then the terminology is flying fast and furiously here, isn't it? All right, what about oh, here we go. Coterminal angles in radians. Now, remember what that means to be coterminal. Like, for example, we had one before. I think it was 220. You know, I'll tell you what, let's make one that's really more convenient than that. One that has an even number of radians. Let's go back and look at our chart for a second. A radians chart. Let's try, how about 3/2 pi? No, that's 180 degrees. 5/4, what is that? All right, good, 225 degrees. And then if I went in, so that's coming in this direction, No, that can't be right. I just realized I haven't drawn it properly. That would have to be down here somewhere. So instead of 225, let's stick with 135. That's better. And because that's equal to, let's see, how many radians would that be? That would be 3/4 pi radians. All right. Going this direction, we'd have negative 2 225, which equals negative 5/4 pi. Okay, so what they're trying to say here is that if you took 3/4 pi and subtract 2 pi, which we now need a common denominator, that'll be 8/4 pi, you're going to wind up with minus 5/4 pi. Okay, this is what we're looking for. In other words, the way we can see that these coterminal angles, how they're related to each other. In fact, if you notice, if you look at these carefully, if you ignore the sign, these two add up to 360. So what they're basically saying is that if you're dealing with radians, to get from one to the other, you simply have to subtract 2 pi, and you'll end up with a coterminal angle. All right, if for some reason you want to do this in radians, you're better off. That's a good question. Since we had angles that add up to 90 and 360, I bet there is a name for that. Boy, I don't know. Okay, let's do it this way. Obtuse angles. No, that's not going to do it. Complementary angles. Supplementary angles. Let's see if there's a third one. Oh, we don't have time to watch a video here. I would be surprised if there isn't a name for that, but I just don't know what it is. So we've got supplementary, we've got complementary. Boy, I don't know. It doesn't look like it. That's a bit of a shocker. How could they not have a name for that? All right, look, let's try this one more time. And then after that, boy, I don't know. I'm kind of starting to wonder if maybe there is no such name. I'm kind of disappointed. Oh, here we go. These guys are pretty good. Oh, yeah. You know what? I'm starting to wonder, maybe there isn't. Yeah, I guess not. Exclamentary. Oh, well, I guess there it is. What was the problem? Why was it so hard to find it? According to Merriam-Webster, who knows what they're talking about, it's called explementary. I've never heard of that word before. Explementary. Well, we better add that to our list. Oh boy, where's my list? Ah, here we go. Explementary. Wow, what a weird word that is. Explementary angles add up to 360 degrees. Wow. That's a new one on me. I've never heard that before, but all right. Anyway, but you had to figure somebody would have come up with a name for that because it could potentially be very useful. All right. Anyway, so what we're building up to here, we don't want to do this now because this is very complicated. we're going to be looking at, basically, this is what this is building up to, is a technique for helping us understand how to calculate the trig functions with the basic standard angles like 0, 30, 60, 90, 180, that kind of thing. But we have to sort of build up a little bit of background before we do this. And so we don't want to do it now, that's for sure. Look at this. It's already looking pretty scary, isn't it? So this will build us up to something called the unit circle, where you'll see how these, yeah, here we go. We're going to really get deeply into sines, cosines, tangents, you name it. And then before you know it, we'll be experts at finding sines and cosines and tangents and all the rest. But this is fairly involved. So we're going to definitely save this for next time. Now, by the way, don't forget, next time means 2 weeks from today. So rather than not doing any math work at all the next 2 weeks, what I would like you to do is go to Moodle, before I forget. And so you're sort of off, but not completely. First of all, make sure you get all your midterms done. Secondly, let's go back to Moodle. And we're going to take a look at what's hiding there, waiting for you. That you should be looking at during the break. And you'll see that we have for you not one, but 2 problem sets for chapter 4, which we just finished. And so you can see, well, this is pretty much exactly what we were doing. And so what I would like you to do is take a look at these and have them ready for the next time that we meet before we carry on with our discussion about trigonometry. So there's 2 of them, 2 complete problem sets. They shouldn't take all that long. They look longer than they really are. So this is all about logs and about exponential functions. So take a look at these 2, have them ready for the next time we meet, and we'll go over these and we'll take it from there. Okay. So in the meantime, I hope you have a good break, such as it is, and I'll see you all in 2 weeks. All right, so find something fun to do to take the place of math, which is going to leave a gaping hole in your schedule, but I'm sure you'll find something fun to do with that time. So, all right, so I'll see you all in 2 weeks then. Okay, see you then.
See you, Professor. Thank you for your time.
All right. Okay, bye. See you then.
Hey, Professor.
Hi.
Hey, can I just I just want to let you know that I sent you my midterm, but there was one question on it that was asking basically prove these 2 functions are inverses. And I did it 2 ways. So one way I did it was I wrote out the inverse of one of those functions, and I said, hey, look, the inverse of this function is equivalent to the g of x. And then another way I did it was I did f of g of x equals x. But I did it 2 ways, and the second way is kind of on the back of the midterm. So I just wanted to let you know that.
Oh, that's right. I'll find it. Don't worry. That sounds good.
Okay, cool. Thanks, Professor Anderson.
All right, see you next time.
Bye. Yep.
Bye.